Hello dear students. So in this video we are going to discuss next important method of analysis of trust, that is your method of tension coefficient. And earlier we have understood the concepts of how to analyze your trust with the help of method of joints and how to analyze your trust with the help of method of section. Okay, so this is a method, and we know the earlier two methods of analysis of plane frames were your method of joint and method of section. Okay, so this is a more general method, and this is called as the method of tension coefficient, okay, which is equally applicable to both plane frames as well as your space frames. Okay, and this method was first introduced by Professor R.V. Southwell. Okay, and this is a neat and systematic presentation of the method of joint. Okay, so in this method, the important is we have to understand the term your tension coefficient. Okay, so tension coefficient for any member in a frame is defined as the pull or tension in that member divided by its length. Okay, so if I am considering one member, so if I need to know what is tension coefficient, so this is your tension coefficient is known as defined as your tension or pull in the member divided by the length of the member. So this is nothing but this is your tension coefficient of the member. Okay. So what is this T? T is your tension coefficient, tension coefficient, and what is this? Capital T. This is your pull, or you can say tension in the member, and the L is your length of the member. Okay. So your tension coefficient will be defined as your pull or tension in the member divided by its length. Okay. So on the basis of this term, we'll further derivate this method. So this is refer to this diagram. This is your coordinate axis x and y axis. Here we are having one member AB, and we are considering pull in this member. So the coordinate of this A joints are x a y a, and coordinates of B is x b y b. Okay, this is our pull or tension in the member AB, and this is our length of the member. Okay, and the angle which is making theta with the horizontal. Okay, so this is the angle which is horizontal, which is theta with the horizontal. And this is our A1 point, A2 point here, and this is a B2 point and B1 point here. Okay, so consider a member AB of pin jointed perfect frame in equilibrium. So under a given system of external forces or reactions acting at the joint, let this tension AB be the resulting pull in the member. Okay, so this is our coordinate XAY at this point, and this is our coordinate XBYB at this point. Okay, so here the component of pull TAB, the component of this tension, or you can say pull in X direction, will be your B know TAB cos theta. So here component of pull TAB will be your TAB cos theta. So what is this cos theta? Cos theta is base upon hypotenuse. So base is AC upon hypotenuse is AB. So base AC will be rewrite as XB minus XA, okay, in the terms of coordinate, and AB is your LAB, length of AB. So pull in X direction will be your TAB XB minus XA upon LA, and we know the pull upon length is known as tension coefficient, which is denoted as small TAB. So TAB into XB minus XA. Similarly, we have our Y component. So this is our Y component of the member AB. So TAB in Y direction will be your TAB sine theta. You can refer this diagram. So this is a member AB, and the Y component will be your TAB sine theta. So what is sine theta? Sine theta is your perpendicular upon hypotenuse. So perpendicular is CB upon hypotenuse is AB. Okay. So CB will be rewrite as YB minus YA. Okay. So here you can see this is your CB is YB minus Y upon AB is your length of member AB. So tension upon or pull or upon length is known as tension coefficient. So TAB YB minus Y. Obviously, the length of the member will be calculated as per Pythagoras theorem. So LAB is equal to under root of XB minus XA whole square plus YB minus Y whole square. Okay. If our member is in compression, then it will have a negative tension coefficient. Okay. When we will work on. So if I'm looking for a joint here, so if I'm considering a joint here A, and this is our external force at this joint XA in positive X direction, and this is our external load YA in positive X direction. If I'm having a member X AB, AC, AD. Okay, so for summation of fx, so or summation of x is equal to 0, we are having at this A joint external load here in positive x direction, so it is plus XA, it is plus XA, plus the tension coefficient of member AB is plus TAB, and the coordinate is XB minus XA, TAB XB minus XA plus TAC XC minus XA. Likewise, we have a TAD. Okay, so which is equal to 0. And similarly, if I generalize this equation, so I am getting XA plus summation of all the tension coefficient, that is summation of Tij. If I am particularly restrict this AB member, BC member, CD member to I and J. What is this I? I is the I refers to the joint under consideration, and J is the joint which is at the other end of the member. Okay, so Tij xj minus xi. So Tij xj minus xi is equal to 0. So this is our equation which will be utilized in your numerical portion. Okay. So similarly, we are having a summation of y is equal to 0. So we are getting ya plus ya. This is our external load at joint ya, and plus summation of Tij yj minus yi, which is equal to 0. So equation 3 and equation 4 are applied joint by joint to get tension coefficients of all members. By multiplying these coefficients with the length of member, the forces in the members are obtained. So here you need to ask to find your forces in all the members. So once you get your tension coefficients, so this is your tension coefficient here. Okay, and you need to find the forces in all members. So you need to multiply the tension coefficient with the length of that member, so you will be getting your results, okay, or your forces. Okay. So let's take one numerical question. Similarly, if we are having a space thrust, then our z equation also comes. So that is zi plus summation of Tij zj minus zi is equal to 0, and the length will be expressed as Lij into root of xj minus xi whole square plus yj minus yi whole square plus xj zj minus zj whole square. Okay, let's take one numerical here. Okay, so you have to determine the forces in AB and CB due to this vertical force P of applied at joint P. So this is your member AB and this is your member CB. Okay, and due to this load at joint B, this is our joint B, and we need to find the forces in all the members AB and CB. So let's take origin at this C here, and Cx and Cy will be your axis of reference here, and the coordinates of three joints, that is your A, B, C, are. So at this joint C, x value is 0 here and y value is also 0 here. So C coordinate is 0, 0. And what is the coordinate of B? B here, we are moving x value of 2 meter here, so x coordinate is 2 and y value is 0. So B coordinate is 2 comma 0. And what is the coordinate of A? So here our x value is 0. Okay, and what is the y value is 1.5. So coordinate of A is 0 comma 1.5, and your length of the member AB will be given as under root of 1.5 square plus 2 square, so it is 2.5 here. We are given with length of BC is 2 meter here. Now considering joint B here, okay, so we know at this joint B, one external load is applied in your downward direction, so which is the minus y direction. Okay, so while writing equation of for this joint B, our external load value will be of minus sign because it is acting in the y direction or negative y direction. Okay, so write the tension coefficient equation for this joint B here. So it is your TBA to XB, XA minus XB plus what is this TBC, XC minus XB. Okay, and in X direction we are not having any external load. Okay, for X direction, so it is plus 0. It is equal to 0, And for y direction, you consider, you refer this diagram only. And for this y, tba, so it is tba ya minus yb plus tbc yc minus yb. And at this joint we are having one external load here in downward direction, negative y direction, so it is minus p is equal to 0. So after substituting the values, we get our xa value is 0 here, xb is 2 plus tbc, xe is 0, xb is 2 is equal to 0. And similarly, by putting all the values, we are getting tba plus tbc is equal to 0. This is our first equation. And 1.5 tba is equal to p. After solving this equation, both equations, tba value we are getting p upon 1.5 here. And by solving one and two equation, we get tba is equal to p upon 1.5 and tbc is equal to minus p upon 1.5 kilonewton per meter. This is our tension coefficient. And for your forces in members ba, we need to multiply our tension coefficient with the length of the member. And the tension coefficient we already calculated here, p upon 1.5 into the length of the member is 2.5, so it is 1.666. By this way, you can find your member force in BC also. This is your tension coefficient in BC, and this is the length of the member in BC. And after solving, we are getting 1.333 P. The minus sign indicating it is in compression. Okay. So if you are having a plus sign, so it is in tension, and if we are having a minus sign, it is in compression. Starting, we are assuming all the members are in tension. Okay, so by this way you can apply the concepts of method of tension coefficient, and based on this your numerical will be solved. Okay, so thank you so much.